Hello everyone, and welcome to our explanatory video regarding the proofs of the Pythagoras theorem. We assume you clicked on this video because you've probably been using the Pythagoras theorem for some time, but are still wondering how it was proven. Well, we can assure you that by the end of this video you will not only know how to prove the Pythagoras theorem, but also how to do it in many different ways. Alright, so let's get down to it. There are many ways to prove the Pythagoras theorem, but for the scope of this video, we'll focus on four main ways, namely geometric, bisectional, trigonometric, and visual. Let's start with the geometric proof. The geometric proof, which is also known as the rearrangement proof, was the first known mathematical proof of the Pythagorean theorem, discovered by none other than Pythagoras himself in the 5th century BCE. The proof uses right-angled triangles and their properties to show that the theorem must be true. We begin with four equal right-angled triangles that are inside the large square with the area of a plus b squared, since each of its sides has the length a plus b. These right-angled triangles are arranged in such a way that they leave room for two more squares, namely a squared and b squared. Since each right-angled triangle has smaller side lengths of a and b, the large square can be denoted algebraically as a plus b squared equals to a squared plus 4 times half ab plus b squared, which can be further simplified to a squared plus 2ab plus b squared. Rearranging the four right-angled triangles inside the large square such that their hypothenuses face inwards creates a smaller square inside of it with the area of c squared, since the hypothenuses of the right-angled triangles each have the length of c. Denoting the equally large but rearranged square algebraically gives a plus b squared equals to c squared plus 4 times half ab, which can be further simplified to c squared plus 2ab. Substituting the equation a plus b squared equals to a squared plus 2ab plus b squared into this equation gives a squared plus 2ab plus b squared equals c squared plus 2ab, which can be further simplified to a squared plus b squared equals c squared. And there we have it. The Pythagoras theorem has just been proven by rearranging a bunch of geometric shapes. You can see it was not so hard, was it? One down and three left to go. Next is the bisection proof. The bisection proof, also called the proof by dissection, is one of the more modern proofs of the Pythagoras theorem and was discovered by none other than Albert Einstein when he was either 12 or 13 years old. This proof uses similar triangles and their properties to show that the theorem is true. We start with the same right-angled triangle as before, with angles alpha and beta and sides AB, AC, and BC. This time, however, we dissect it into two new right-angled triangles at point H, which we will call green and blue respectively. Since angles alpha and beta must add up to 90 degrees, you can see that the two new triangles have the same angles as the original triangle. Therefore, all three triangles are similar to each other. Thus, we can establish the following mathematical relationship regarding their sides. Side A divided by side AH of triangle green equals to side BC divided by side BH of the original triangle. And side BC divided by side BH of triangle blue equals to side AB divided by side BC of the original triangle. Rearranging both equations gives AC squared equals to AB times AH, and BC squared equals to AB times BH. Once you have this, you can add up both equations, which gives you AC squared plus BC squared equals to AB times AH plus BH. Since AH plus BH equals to AB, then AC squared plus BC squared equals to AB squared, which, if we remember from the beginning, are the three different sides of our original right-angled triangle. In other words, a squared plus b squared equals c squared. Next up is the trigonometric proof. This proof is one of, if not the newest proofs of the Pythagoras theorem as of today. This proof was discovered by senior students Kelsey Johnson and Akia Jackson at St. Mary's Academy in New Orleans in 2023 to win a school-wide math contest with a prize money of $500, believe it or not. But hey, Einstein found the bisectional proof when he was just a teenager, so I guess everything is possible when it comes to brilliant minds. Alright, so this proof uses trigonometry, similar triangles, and infinite geometric series to prove the Pythagoras theorem. Again, we start with a right-angled triangle with sides A, B, and C, and complementary angles alpha and beta. Using the basic sine function on angle beta, which is not derived from the Pythagoras theorem, we get sine beta equals to B over C. Now we use the sine rule on the same triangle after it's reflected in order to describe sine 2 alpha. Don't worry, the sine rule is also not derived from the Pythagoras theorem. Doing so, we get sine 2 alpha over 2a equals to sine beta over c. Since we know sine beta equals to b over c, substituting it into the sine rule equation gives us sine 2 alpha over 2a equals to b over c, which can be rearranged to c squared equals to 2ab over sine 2 alpha. And this is how we define c squared using trigonometry. Turning the reflected triangle into a waffle cone, which is a right-angled triangle composed of infinitely similar right-angled triangles, gives us the following mathematical relationships. Sine 2 alpha equals to u over v, since u is the opposite side and v is the hypotenuse side of the waffle cone, and that u and v can be expressed as the following sums of infinite geometric series. The detailed method used to get these sums of infinite geometric series is beyond the scope of this video. Soon we will publish another video with a full-fledged explanation of this proof, covering it from top to bottom. Now back to the proof. By using the rule for the sum of infinite geometric series, namely that, we get that u equals to 2abc over b squared minus a squared, and v equals to c times a squared plus b squared over b squared minus a squared. Substituting both equations into the equation sine 2 alpha equals to u over v gives sine 2 alpha equals to 2ab over a squared plus b squared. Substituting that into our initial sine rule equation, namely 2ab over sine 2 alpha equals c squared, gives us c squared equals to 2ab over 2ab over a squared plus b squared, which, if simplified, equals to a squared plus b squared. And there we have it. A squared plus b squared equals c squared. Finally, let's explore a visual proof. Visual proofs use diagrams, pictures, and real-life objects to make the theorem clear and understandable. The visual proof we will showcase in this video is a very creative one, since it uses fluid laws to its advantage for the purpose of reshaping areas. The proof that you see in front of you right now shows how the areas of the squares of sides A and B equal to the area of the square of side C using water. Since the water in squares A and B perfectly fill square C when flipped around, it can be visually deduced that a squared plus b squared equals c squared. This visual reshaping helps us understand the relationship between sides of a right-angled triangle in a more intuitive way. To sum it all up, the Pythagoras theorem has dozens if not hundreds of different proofs, each providing a unique perspective on its validity. This phenomenon truly shows us that mathematics still has so many areas that are left unexplored. It does not matter how old a mathematical theory might seem, if you investigate it deep enough, you will find a domain of unexplored theories, as was the case with the two senior high school students who found the full-fledged proof to the Pythagoras theorem after more than a century of neglect. Thank you for joining us today. If you have any questions, please feel free to ask them in the comment section below. And don't forget to stay curious.